Hi guys, it's Miss Mangello. We are up to the point where I want us to take all of the demos and the ideas and the conversations and really link it to more concrete problem solving with your Regents curriculum. So we definitely had conversations that allowed us to think about and talk about the relationship between volume and pressure. And in particular, that is this relationship was studied and determined to be what it is by a person by the name of Boyles, and therefore it was named Boyle's Law. And not that you have to remember that, but what you do have to understand and think about is that volume-pressure relationship. So here, instead of us looking at the vacuum chamber, instead of us looking at marshmallows and shaving cream, we're looking at a piece of equipment here that has a weight on it, okay, and the weight is exerting a pressure, and we have an initial amount of space that's being taken up as 1 liter, and then we have a situation where the amount of pressure being placed on this gas is now doubled, and as a result, the amount of space is halved. Okay, and what you can see is that the original weight, the one weight, pushes on these molecules, and they push onto this millimeter of mercury and show you that it measures 760 millimeters of mercury of pressure. That's how much pressure is being exerted by the molecules within this container. And understand, when the molecules crash into one another, then they exert a force, and all of those molecules are pushing against this tube of mercury to keep it at the height of 760, at 760. Then if we double the pressure, then the container, the amount of space, has halved. But just like when we looked at the red dots, there is less space, so therefore there's more collisions because we have a set number of molecules inside the space, right? And so that's our moles that are being held constant, and also our temperature is held constant. And you have the space because you've increased the pressure, and therefore, look at this. This pressure has doubled. So let's take a moment to really look at how the math is involved. So a little bit more of an extension from last night is when we look at this mathematical representation of this relationship between volume and pressure. So what we would do is we would write that the volume equals an inverse representation 1 over the pressure, and this only exists because it's a constant, okay? And we represent that with a K. And the constant we talked about last night, it means that your N, that was the symbol for the moles, the number of particles, right? Inside here stays the same, and also the, whoops, hold on. The number of moles stays the same, and the temperature stays the same. So that's what this K is representing as the constant, because we're looking at just how the volume and the pressure relate to each other. So here's how this gets a little mathy, okay? You have to start to look at what this is representing for you. So you've got volume, and we said it's inversely proportional. So in other words, when I have the pressure and I increase the pressure, then the volume goes down, right? This was the first situation with the pressure, and then this is the new situation, so there's double the pressure, but then we had half of the volume. So we doubled the pressure and we halved the volume. So how does that make sense if I go and I check this out? So if these two things, the volume and the pressure, have to equal each other in this relationship, then the only way that this number right here is really going to get smaller is when you make the bottom of it, the denominator, bigger. So this is very much relying on your understanding of math right now. So if we take some time to add some numbers into this, say I were to pick the number 10, and you set it equal to something. So in order for 10 to be equal to what's on the other side, and say the other number on the top, I made 100. Well, really, how can I make the 100 equal to 10? Well, the only way I can do that is to put a pretty big number on the bottom, right? I have to do 10 divided into 100, and that would be 10, so the 10 equals 10. So you have a fairly big number on the denominator. Now, say we had a 1 over here, and we decreased the volume, and we still have 100 on the Okay, so we have the 1, and we're setting it equal to 100 in the numerator, but we really want the 1 on the left to equal the 1 on the right, and the only way we could do that is if we were to make this denominator really large and and divide the 100 by 100, because we agree anything divided by itself is 1, so now the 1 equals the 1. So you can see that when you set up the volume equaling 1 over the pressure, when the volume goes down, the pressure is inversely proportional, the pressure goes up. So to make sure you see this clearly, the volume and the pressure are related, so when the volume is going down, the pressure increases, but when the pressure increases, it's making this whole number smaller, so that's an inverse relationship, so that the left and the right side of the equal sign stay equal to one another. So let's plug some numbers into this chart right here. Okay, I think this might help you out. So if we were going to make the pressure and the volume equal to 20, 1 times what will give you 20? Well, 1 times 20 will give you 20. And then if the pressure were 2, and the volume were 10, 2 times 10 gives you 20. And if the pressure were to go up to 4, and we had to keep the constant at 20, then 4 times 5. So although the pressure is going down, the volume is going up. But when the pressure goes up, the volume now can go down. And as we continue along, 10 times 2 will give you 20, and 20 times 1 will give you 20. So you can see that the relationship between these numbers are inversely proportional to one another. So let's pay closer attention to the relationship that we see going on here. So if the pressure doubles, then the volume just halved itself. 10 is half of 20. And if the pressure quadruples itself, then we're looking at a situation where oh my, I apologize. The volume quarters itself. So quadruples to quarters. Pressure doubled, volume halves. Pressure quadrupled, volume quartered. So we did this in class, but let's take these points and plot them on this chart, volume versus pressure. So if our pressure is at 1, and our volume we'll put up at 20, and we put a little dot. And then we have the pressure at 2, and then we need to put the volume at 10, So half of 20 is 10. So we put it there. And then we have pressure of 4. So we do 3, 4. And then the volume is at 5. So 4 and 5 is like there. And then we have the pressure at 5 and the volume at 4. And then we have the pressure at 10. So I'll go 6, 7, 8, 9, 10. And the pressure's at 2. And then we have the pressure at 20 and the volume at 1. We saw this. We saw this in class when we were using that syringe animation that changed the pressure and the volume. So as you can tell, these lines, my drawing with this pen is not the best, but these lines will continue to try to get closer and closer to the x-axis, and over here closer and closer to the y-axis, but they never quite touch it. And we're going to spend some time, probably next week, talking about why that is and what occurs. But needless to say, we definitely have a situation where we've drawn a curve that shows an inverse relationship, and we over here, we doubled and we halved and we quartered and we quadrupled and then we quartered. So again, if you were to look at this, if one goes up by 3 times, the other will go down by 1/3. And as you plot these points and look at this curve, and as you fill in this chart, you can really get a solid hold on the relationship that exists between the volume and the pressure, as long as your temperature and your number of moles are held constant. Hello. So before we start a problem utilizing the ideas that we've learned, I do need to point something out to you. So we just established and agree that pressure equals, I'm sorry, hold on a second. Getting ahead of myself. Volume equals 1 over the pressure times the constant. And what you saw last night actually was that you end up taking, I keep fighting with this, hold on, that you end up taking this P and moving it up over here to get it out of this situation, now that we've explained the relationship and how it works. And you end up setting it equal to K being your constants, okay? And then there's another law that we talk about, and that is one that involves volume equaling the temperature times the constants. So mathematically, to remove the temperature, you have got to divide you've got to divide by the temperature, and you divide by the temperature over here. So you have a situation where volume is divided by temperature, and that's how you set up that gas law. So it looks more like V over T equals the constants. So we can do something called combine these, and I'm going to combine them, and we could talk more about it, but we're going to combine them because in a question like this, it says, if the volume of a certain obscene gas, we've all smelled those, is 480 milliliters, and the pressure is decreased from 4.3 atmospheres to 1.2 atmospheres, what is the new volume of a gas at a constant temperature? So what we do is we take our volume and our pressure, which we just got from right over here, and we divide it by temperature. And we know that that is a setup that we can consistently use. And what you do is when you see something is held constant, well, you just kind of don't use that one. during the solution of the problem. You just worry about your volume and your pressure. So let's go check out table T. Here's table T. And we see our density formula we're familiar with, our percent error formula, okay, our heat formulas which we've used, temperature conversion into Kelvin, and right here is this combined gas law. So it's pressure over volume divided by temperature, and pressure over volume divided by temperature. And the reason they use these little subscripts, these little numbers, because when you do a problem, you're going to be given an original situation, and you've got to figure out what happens when something changes and what is the new relationship between these two. So it'll make more sense when we do our problems. So let's go back and look at the problem. Okay, let's set up the problem. We're going to need our formulas. So a quick little way to give yourself a way to remember it: Vice President, VP, over temperature of the current situation, what you're given, and then you have Vice President over the new situation, or what you're about to determine. Okay, so let's pull information out of the problem. So if the volume of a certain obscene gas is 480 milliliters, so we know based on the unit, the milliliters, that's going to be your first volume, and the pressure is decreased from, so 4.3 atmospheres to 1.2 atmospheres. So that means this is where it starts, 4.3 atmosphere, and it changes to 1.2 atmospheres. So you can take your 480, and you're going to represent it with milliliters, and your first pressure is the 4.3 atmospheres, and you're going to multiply it by 4.3 atmospheres. We're not going to be using temperature in this problem because it's held constant. And you set it equal to the new situation. So the atmospheres are what changed, and you want to find out what the new volume is. So you put your volume over here, because that's your question mark, and you put your new pressure over here, 1.2 atmospheres, and then you solve like we've been solving. Okay, so let's do some of the algebra that's necessary. So we're going to get rid of what is on the right side of the equation. And a way to do that is to multiply by 1 over 1.2 atmospheres. And whatever you do to the one side, you do to the other side. So then that looks like this. 1 times 1 over 2 atmospheres. And what that turns into is 480 milliliters times 4.3 atmospheres divided by 1.2 atmospheres. Okay, so an important thing for you to learn to do is this idea of the setup, because on the regions, they'll ask you questions when they won't even want you to necessarily plug it into your calculator and get a final answer, but what they'll want to know is that you can read this problem, you can pull out the initial volume, you can pull out the initial pressure, you understand that there's a new pressure, you understand that you're solving for a new volume, and they want to know that you know how to isolate this new volume by itself algebraically. So the best way to do that and represent that is to get in the practice of writing the setup. And the way to do that is put the two things with the like units together. So you put 4.3 atmospheres over the 1.2 atmospheres, and you show that you're multiplying it by 480 milliliters. And that right there will get you the points that you need to answer the questions when they ask you to solve for, set up the equation. And what would you have to do to solve for the new volume. Now, let's also plug away and figure out what this ultimately comes to be and what our new volume becomes. Okay, so now that we have our setup, we can look at it and see if it makes sense. So the atmospheres would cancel. You'd be left with a unit of milliliters, and your new volume should be in milliliters. Now, to plug it into your calculator, you would do your 4.3 divided by 1.2, and then multiply that answer by the 480, and what you should come up with is that your volume is equal to 1720 milliliters. And just to make sure that everything we spent time discussing about earlier in the relationship, that idea that if you double the pressure, you half the volume. So if we look at this, 1.2 atmospheres compared to 4.3 is about 3.5 times smaller. Okay, so you've decreased the pressure by about 3.5 times, and doesn't it make sense that your original volume was 480, and now this new volume is about 3.5 times bigger? So it makes sense because you made your pressure 3.5 times smaller, so then your volume became 3.5 times larger. So there's that inverse relationship in play. And if you want to write your answer over here, 1,720 milliliters. Now, what I ask is that you try the next one on your own, and we'll talk about it tomorrow. Have a good night.